In this video, I will show you how to find the intervals where a function is concave up or concave down. I will also show you how to find the points of inflection where a function changes concavity. This video is actually the second half of the lesson. So for more practice, you should probably watch the first half, and I will try to put a link in the upper right hand corner. Go ahead and watch that first. And come back to this one though. Before we take the derivative of f of x, let's rewrite it a little bit to make it easier. First of all, the square root of x is the same thing as x to the 1/2 power. But wait, that's not all. Let's take this x to the 1/2 power and move it out of the denominator. So then we have f of x is equal to x plus 3 times x to the negative 1/2 power. Now we can start doing the first derivative. We will use the product rule. So according to the product rule, you take the derivative of the first factor while leaving the second factor alone. But the derivative of x plus 3 is just 1. So I took the derivative of the first factor and I left the second factor alone. Then you put a plus and you go through it again. But the second time through, you take the derivative of the second factor and you leave the first factor alone. So I'm going to copy down my x plus 3. And now I will take the derivative of x to the negative 1/2 power by putting the negative 1/2 in the front and then subtract 1 from the exponent. So I'm subtracting 2 over 2, so this will be negative 3 over 2. Now it is time to take the second derivative, f double prime equals. So the derivative of x to the negative 1/2 power will be negative 1/2 times x to the negative 3 over 2 power. Just did the power rule. As we move on to this next pair of factors, we will do the product rule again. So again, we start by taking the derivative of the first factor while leaving the second factor alone. But the derivative of x plus 3 is just 1. But for now we leave the second factor alone. So negative 1/2 x to the negative 3 over 2 power. You put a plus and then you go through it again. This time around you leave the first factor alone. So there's the x plus 3. And you take the derivative of the second factor. So here comes another power rule. So negative 3 over 2 times negative 1/2 is positive 3 over 4. Now I need to subtract 1 from this exponent. So I'm subtracting 2 over 2. So this will be negative 5 over 2. So this is the second derivative. We do need to simplify this to make it more usable. Of course, this 1 sitting here in the front isn't really doing anything. The parentheses are not needed either. Maybe you can see that we have like terms here. These are actually exactly the same term. So we have negative 1/2 x to the negative 3 over 2 power and another negative 1/2 x to the negative 3 over 2 power. If you combine these, you're going to get negative 1/2 x to the negative 3 over 2 power. So let's do that. Also, let's distribute this to both of these terms. So far, I have combined these two terms into one, and that's where this term came from. I'm going to go ahead and do the distributive property now, but I figured I should do it on camera so you can follow where things are coming from. So I'm going to have the 3/4. So I'm multiplying the 3/4 x to the negative 5 over 2 power times x. I went ahead and called it x to the 2 over 2 power so you can follow what's happening there. So I will definitely have the 3/4 in the front. When you multiply these variables, you add the exponents. So 2 over 2 plus -5/2 will be -3/2. So I have x to the -3/2 power. Now I am multiplying times the 3, and this is like having 3/1. So I'm just multiplying straight across, and I will have 9/4. So I have 9/4 times x to the -5/2 power. Once again, we have like terms with the -3/2 power. So I will think of this as -4/4 x to the -3/2 power. So on the next step, we will be adding -4/4 plus 3/4. So this should be -1/4 x to the -3/2 power. So far so good, but we can make this even simpler by factoring out an x. Notice that both of these terms have x, so we should be able to pull some kind of x outside of parentheses. It's just a matter of what the exponent should be. Always go with the lower exponent in the previous step. So -5/2 is less than -3/2. So I'm going to pull out x to the -5/2 power. Now I need to figure out what will be left inside the parentheses. But remember, when you factor something out, you are really dividing by that thing. And when you divide, just like when you have n to the 6th power divided by n to the 3rd power, this is n to the 3rd power because you subtract the exponents. So keep that in mind. When I divide by this x to the -5/2 power, I need to subtract -5/2 from each of these exponents. But this will be a little bit weird. When you subtract a negative, that's really addition. So I'm going to put plus 5/2, but I'm actually subtracting -5/2. We still have the coefficient in the front, so I'm just going to bring down my -1/4. But -3/2 plus 5/2 is 2/2. So this would be x to the 2/2 power, but that would be silly. This is just x to the 1 power, or better yet, just x. Moving on to the next term, I'm going to bring down the 9/4. But then -5/2 plus 5/2 is 0. The 0 power makes this a 1. So I don't really have to write anything. So I don't need that much space in these parentheses. So we have this so far. By the way, I could also just look at this as I factored out x to the -5/2 power. So you could just think of it as I took this away and put it out here, and now it's gone. I would normally skip this step. I'm only showing it for instructional purposes. I just took the x and put it up in the numerator. So this is the same as -x/4. I did that to make it obvious. On the next step, I'm combining these into one fraction. You see they have a common denominator. So I'm going to end up with -x plus 9/4. There is only one more thing we need to do to simplify. Because this has a negative exponent, I can take this x to the -5/2 power and drop it down to the denominator. I'm going to put it right here. So finally we have this. In this form we are able to find the special numbers of f double prime. We need the values that will cause f double prime to equal 0 and the values that will cause f double prime to be undefined. F double prime will equal 0 when the numerator is equal to 0. So we set -x plus 9 equal to 0, and we end up with x equals 9. F double prime will be undefined when the denominator is equal to 0, but if we set this equal to 0, we can just immediately tell that the only value of x that will cause this monomial to equal 0 will be 0 itself. So these are the values that go on the number line, which form the sign chart. So I'm placing those special numbers in order on the number line. Looking at my expression for f double prime, I have two factors that I need to account for, so I will need 2 rows on my sign chart. Now we need to determine if these factors are positive or negative in each interval. By the way, make sure you label your sign chart as f double prime. Let's start with negative x plus 9. If you set this equal to 0, you get x equals 9. So 9 is the cutoff. What happens if we choose a value that is less than 9? For example, 0. If you put in 0, you would just be left with positive 9. So values less than 9 will give you a positive result. Values greater than 9 will give you a negative result, which makes sense because imagine that x was 10, then we would have negative 10 plus 9 would be negative 1. So of course, setting 4x to the 5 over 2 power equal to 0, that's where we got the 0. So this is the cutoff. For values that are less than 0, well, wait a minute. This 2 in the denominator means square root. So guys, this expression really is the same as the square root of x to the 5th power. You cannot take the square root of a negative number. So values less than 0 will cause this factor to be undefined. If x is greater than 0, then this expression will be positive. So we'll put a positive here and here. Now let's consider the overall value of f double prime. If the numerator is positive but the denominator is undefined, then f double prime is undefined. If we have a positive divided by a positive, that's a positive. If you have a negative divided by a positive, that's a negative. But remember, if f double prime is positive, the function is concave up. If f double prime is negative, the function is concave down. That means the function will be concave up in this interval from 0 to 9, and it will be concave down from 9 to infinity. Let's write up what we have so far. So we would say f of x is concave up from 0 to 9 because f double prime is greater than 0. Don't forget the justification. F of x is concave down from 9 to infinity because f double prime is less than 0. But we are also supposed to identify any points of inflection. We notice that f double prime goes from positive to negative at x equals 9. So we add f of x has a point of inflection at x equals 9 because f double prime changes signs. Let's try one more, this time with some trig functions. We will start by finding f prime. The derivative of sine is cosine. The derivative of cosine is negative sine. So there is the first derivative. Now let's find the second derivative. The derivative of cosine is negative sine. And the derivative of sine is cosine. So this is the second derivative. This second derivative cannot be simplified any further, so it's time to move on to finding the special values that will cause f double prime to equal 0 or cause f double prime to be undefined. Sine and cosine are defined for all real numbers, so we don't have to worry about this one. So we just have to set the second derivative equal to 0 and solve. This one takes a little bit of intuition. We don't have factors, so we can't use the zero product property and just set parts of this equal to 0. Let's try adding cosine to both sides and see what we think. So now we have sine x is equal to cosine x. All right, now think about this for a second. If I took away the negative sign and asked you to think of a value, an angle, where sine and cosine are both equal, what would you say? You would probably come up with this. How about x equals pi over 4? This is the one angle where sine and cosine are equal, because sine of pi over 4 is equal to radical 2 over 2, and cosine of pi over 4 is also equal to radical 2 over 2. So keep that in your mind for a second as I put this negative sign back. So this means that sine and cosine are the same. They have the same value, except for one is positive and one's negative. I think we can still use pi over 4, but we will have to think of pi over 4 as the reference angle as opposed to the final answer. There are 4 angles on the unit circle that have a reference angle of pi over 4. There's one in every quadrant. Let's write down the sine and cosine of each of these angles. Of course, cosine is the x value, sine is the y value. So in this quadrant, we will have radical 2 over 2, comma, radical 2 over 2. The cosine and the sine are the same. We're looking for the values where the cosine and the sine are the same, except one's positive and one's negative. Of course, that will happen here in the second quadrant, where the x value is going to be negative. So here in the second quadrant, we have negative radical 2 over 2, comma, radical 2 over 2. So this is one of the angles that we're looking for. I should highlight this in some special way. And then in the third quadrant, we have negative radical 2 over 2, and another negative radical 2 over 2, because both x and y are negative in the third quadrant. So that's not one of the angles that we're looking for. And then finally in the fourth quadrant, x values are positive, so we have radical 2 over 2 for cosine, but y values are negative, so we have negative radical 2 over 2 for sine. So this is another location where sine and cosine are the same, except one's positive and one is negative. So these two angles will be the answer. So just very quickly, what are these angles? Well, here in the second quadrant, this is 3 pi over 4. You could count it if you wanted to. 1, 2, 3 pi over 4. So we will just write this down. One solution is x is equal to 3 pi over 4. And then here in the fourth quadrant, this is 7 pi over 4. So these are the two special numbers. Here are the two special numbers in order on the number line. Because we are limited to the interval from 0 to 2 pi, I'm going to add 0 on the left and 2 pi on the right. Make sure you label the sign chart as F double prime. Now it's time to figure out if this expression is positive or negative in each of these intervals. First, let's pick a value between 0 and 3 pi over 4. So that's going to be somewhere in here, and why not just pick pi over 2? So this would be negative sine pi over 2 minus cosine pi over 2. Sine is the y value, so the sine of pi over 2 is 1. So we have negative 1 minus. Cosine is the x value. Cosine of pi over 2 is 0. So we have negative 1 minus 0, which is just negative 1. That means the expression is negative in this interval. For the next interval, we need a value between 3 pi over 4 and 7 pi over 4. So that's going to be somewhere between here and here. why not use pi? So we have negative sine pi minus cosine pi. Sine is the y value, so sine of pi is 0. So this will be negative 0 or 0. Cosine is the x value, so this is negative 1. So that would be minus negative 1, which would be positive 1. So f double prime is positive in this interval. Finally, we need a value between 7 pi over 4 and 2 pi. Luckily, I'm noticing that 2 pi is included in the interval with a bracket, so I'm going to go ahead and use 2 pi itself. So that would give us negative sine 2 pi minus cosine 2 pi. Sine is that y value, so sine is going to be 0 here, so this will be 0. Cosine is the x value, which is 1 in this position. So 0 minus 1 is negative 1. That means f double prime will be negative in this interval. This expression is f double prime. We know that when f double prime is negative, the original function is concave down. And when f double prime is positive, the original function is concave up. So therefore, the original function should be concave down from 0 to 3 pi over 4 and from 7 pi over 4 to 2 pi. And it should be concave up between 3 pi over 4 and 7 pi over 4. Let's go ahead and write that up. So we would say f of x is concave up from 3 pi over 4 to 7 pi over 4 because f double prime is positive. And f of x is concave down from 0 to 3 pi over 4 and from 7 pi over 4 to 2 pi because f double prime is negative. We also need to mention the points of inflection. Notice that f double prime goes from negative to positive at 3 pi over 4, and it goes from positive to negative at 7 pi over 4. So we say f of x has a point of inflection at x equals 3 pi over 4 and x equals 7 pi over 4 because f double prime changes signs.